looking at today and Monday discrete probability distributions, and then we'll do continuous. So just in terms of the difference between them, a little bit of an introduction here. So data are pieces of numerical or quantitative or other qualitative information from which inferences can be made. The property for which the inference is made is to what the data refers and is called a variable. So for instance, the city of Calgary may be interested in determining how much water is being used on lawns during July and August, and then use that information to set bylaws in place. The variable, is it continuous or discrete? So when you think about amounts of water being used, it can be a decimal value. It really depends on your measuring device, but you could have, basically it's a continuous variable, okay? It's not 1 liter one day, or 1 milliliter one day, or 1 liter, whatever it is. So this would be considered continuous. So just be aware of that. Stats, the branch of math that deals with collection, organization, analysis, and interpretation. Probability, a measure of the likelihood of the occurrence. And often we talk about these are combined. If you take sometimes at university it's a specific stats, sometimes it's stats and probability, but they're usually combined. So we really are doing a lot of probability in this unit. We're reviewing some of that data collection stuff though from Math 20. So you've collected data, organized data, and analyzed in previous courses. Probably in science courses, you've done more of the collecting. In math, we kind of gave you the data, but you've probably done a lot in your science classes. So either by surveys, observation, research, experiments, you collect your data, and you collect it from a sample, usually, of the entire population, right? So it's very rare that you can do an entire survey of an entire population. I always think about that. The word that we use for that kind of thing would be a census. So when the government sends out a census, they're getting information from every single household. Okay, and there's apparently a fine or a penalty if you don't answer it, because they want it from every person in the population, as opposed to just randomly surveying certain people. That would be a sample of the population. So organization, we can use tables and graphs, frequency table, cumulative frequency tables and graphs. You did that back in Math 20. And then you want to analyze. So often mean, median, mode, sometimes quartiles, interquartile range, percentiles, and standard deviation. Okay. So back in, really, when you did normal distributions, again, that was back in Math 20 for you guys. We used to do it in 30, but it was in 20. That's a continuous probability distribution. Remember that bell curve? It's a continuous curve, right? So really, you've already done a lot of work with continuous with standard deviation, and then we're continuing more with non-normal distributions in this unit. Okay? So variable for which the data is collected is either discrete or continuous. Discrete. So capital X is naming the variable. Okay, so in this case, X is going to be a value belonging to a finite or countably infinite. So it can go on forever, but those values have to be exact, if you want to think about it. Usually, they are whole numbers. Continuous variable takes on any possible real number in an interval. So X is sort of the name to it, and then the values, X equals all the values that it could be. So if X is the amount of water in a 50-liter rain barrel, then X is, so think about that, water in there, depending on your measuring device, you can get any decimal value, right? So that's a continuous variable.
Okay, and so where x has a range of values, if it's empty, between 0, and if it's full, 50 liters. And x would be an element of the set of real numbers. If x is the number of automobiles in the Henry Wisewood parking lot on any given day, then that is discrete. You can't have part of a vehicle if you want to actually use it. Okay. So x would have a range of values between, well, 0. I don't know how many cars do you think parking lot holds? No, I'd say 200 to 300, maybe 200. There's like 70 staff, 70 or 80 staff, and then all those parking stalls there. So let's say 200. I don't know. In this case, these we don't want real numbers, right? We don't want decimals. So these would really be could be 0. So we want them to be whole numbers. In IB, they use N for whole numbers. So I've started marking your assignments or your partner test from this week. And so I'm using the marking guide that they have for those questions. And so I was reading through it. It's not as easy as just marking when you do it, but in any case, they do say in there that, say for example, you use the Alberta curriculum, so you use W for whole numbers, they will accept that. So they know that students are learning all over the world, so and different places have slightly different notation. So don't worry if you use W, or say for integers you use I and IB uses Z. They'll be fine with that. Okay? So remind you. Okay, so sample versus population. We talked a little bit about this already. Population may be so large and impossible to collect the data from the entire. So we use a sample. If the sample is chosen well, it is considered to be unbiased. So a random sample that's chosen properly, so that you can summarize that information and for the whole population. Okay. Methods for finding statistical variance and standard deviation are different, slightly different for sample and population data. But we're not going to get into those differences. You have to take a university course to know the differences between that. So in terms of the formulas, so mean, we know you add up all the data values and you divide by how many there are. So all that this is showing is it's in sigma notation, summation. Adding up all the data values, dividing by how many there are. This mu is actually for a population, and so it's kind of interesting because in your data booklet they actually use, now in the new data booklet, they use X with a bar, which means mean. So either of these mean the mean. And then they use mu in other places for the mean. So either one of those, your calculator uses this, and a lot of times that's what you're going to end up using. So just be aware of that. This here is for, say, a frequency chart that you might have. If you have, so say you have your X values are 1, 2, 3, and how many, the number of these. So say you're rolling the die and you roll 10 ones, or you roll 3 2s, or 5 3s. So that's just saying you need to figure the chart here is the fast way of showing them. You don't want to go 1 1 1 1 1 1 1 in your calculator 10 times, and then 3 2s, and then 5 3s. You multiply these together, so that's what that means. F is frequency for that particular data value. Okay, so then the total number of items
is the sum of all the frequencies. Okay, so sometimes they'll give you information in terms of a mathematical statement, like a summation like that. So that's saying that the sum of data values from 1 to 20, so 20 data values is 226. Find the mean. So all you do is divide. You can do that. You can look at the next one. I'm just going to try to get a calculator out here for some later stuff. All right, so used to doing vectors. So x with a bar. So the formula is from 1, in this case, to 20 of xi over 20. And we know that it's 226 divided by 20. So here, now, it didn't say what to round to. So you'll get 11 point. So this is when it doesn't say in your IB questions, it won't say what to round to. You go 3, what they call significant digits. You're not using, like, to me, it's kind of a weird, because when I think of significant digits, I think of, okay, you find data or you're given data, you put it in a formula and you look at the significant digits in that. This is, I guess you're finding data. It's 3 digits, but anyway, 3 digits. If you're not unsure, that's what you do. Okay, so 11.3. Okay, next one. A CD. Do you guys even know what a CD is? Hopefully. Okay, good. At least I don't have cassette in there. Do you know what a cassette tape is? Okay, some of you do. Good. All right, so the total cost for 60 CDs is this. Determine the mean price of these. And then another 40 of them have a mean price given. Then you want to find the mean of all 100 of them. So first one here, mean, actually I'll just use notation, x of first 60. So that's $773.40 divided by 60. Figure that out. Okay. Then for the mean price of all 100, okay, well, we already know the total of the first 60. Okay, we don't know the total of these 40, right? So we need to be careful here. Don't just add in $11.64, right? It's called what we call a weighted mean. You have to treat each item correctly. If I just add this and the total of those and divide by 2, that would say there's equal numbers of each. But there's 60 that have a total of this, and then 40 that have an average of 11.64. So you want to find the total of those 40, and then you divide by 100. Now, this is money. So, because it's money, price, this would be an exception. I'd actually go to 2 decimal places because it's money. 40 times 11.64. Okay, so
And here's what I was talking about before, our frequency chart. So calculate the mean. Yep.
So like a mean price of a further 40 CDs is 11, as in like each CD in that 40 is like 11.
Right. Because it's the mean, so that's the average. Yeah. Some might be higher, some might be lower, but when you find the mean, that total amount is going to be the total of 40 times 11.64. Okay, so then here, you can do this separately, right, or do it by hand, I should say. Or remember back in your calculator, this is kind of an older version of the calculator just because my computer's messed up. So let's see if I can, okay, I have here. So you can go to your list and enter your X values in the first one. So 2, 3, 5, and 8. Oops. 2, 3, 5, 8. And then your frequencies, 5, 6, 1, and 2. Okay. Quit out of that. And then we do a calculation, stats calculation, one variable stats. Okay. Your newer calculators will prompt you. You have to tell what data you're using and what list it's in and your frequencies. In mine, I actually have to list it. So I have to go L1, comma L2. So if I just enter it and calculate, it will just give me the mean of this particular data in the first list. But for mine, I have to do it like that. Okay. And then you should get 3.5 for your mean. Which if you didn't say to include this list here, the mean of these would be 1018 divided by 4 is 4.5. So if you got 4.5 for the mean, you didn't tell what the correct list to use. Okay, so the mean is the first one, 3.5. All right, so the variance is really the square of the standard deviation. So as I said, we've talked about standard deviation with normal distributions. I'm sure you've done it in probably more bio than any other sciences, but I'm not sure. Maybe you can. In any case, the variance is the square of the standard deviation, but really you calculate the variance first. So what is it? It's the sum of the squared distances of the data values from the mean divided by the total number of data values. So here's your mean. Again, they use mu here. So you take each data value, subtract the mean, square it. Next data value, subtract the mean, square it, for all of them, and divide by the total number. You get the variance. Okay. Another way of calculating, if you were to expand that out, would be the sum of the squares of the data values divided by the number of them, and then subtract just the mean squared, not over n, just the mean squared. Again, so here what they put in your data booklet is actually this one here. This is if it's just straight data, no frequencies. This is if there's frequencies for each one. Okay, so this is in your data booklet. You're really going to end up using this one most often. You're not going to have to go through each data value and calculate the difference there and square them. You're really going to use the second version. And that's what the questions that are coming up.
Okay, so you may have to convert back to this page. And then, as I said, just the square root of the variance is the standard deviation. Right? When you're doing that in your calculator, they use sigma with an x next to it. That's their notation. But really it's just sigma. That's a lowercase sigma. Okay, so here's an example given that n equals 10. So that means here, this n would be 10. Okay, so those 10 data values have a total of 410. The variance is 12. Calculate the sum of the squares of each data value. So again, that's 10. Okay, so look back at your variance formula here. Okay, really, it's not a frequency, so we can just use this one. We know this. Okay, we're trying to find this. We know this, and we can figure out what the mean is because we know the total of the 10 terms. We can just divide them by 10. Okay, so here mu or x to the bar is going to be equal to 410 over 10, so 41. So then the variance equals the sum of the squares of each data value over 10 minus 41 squared. And then you just rearrange your formula. So that's going to be 12 plus 1,681 equals actually, and then times by 10. So then this one, given two sets of data. So for the boys in this particular class, mean of 31, standard deviation of 6.2. Mean mark for the girls, 36, standard deviation of 4.3. Determine the mean mark and standard deviation of the whole class of 25 students. Okay, so think about what you want to end up getting here. So the mean mark, we can do that one pretty straightforward because it's very similar to the previous page. So, so mean for the boys is 31. Mean for the girls is 36. Okay, so the mean total, well, there's 12 boys, so 12 times 31. And there's 13 girls times 36 divided by the 25 in the class. Then for the standard deviation, we need to know the sum of the squares of all the data values. Okay, so we're going to have to solve that just like we did here.
we found the sum of the squares of the data values. We're going to have to do that for the boys and for the girls, and then add them together. Okay, so kind of like this one. So for the boys here, we would have, we're going to have standard deviation of 6.2. Now, standard deviation, that means the variance is the square of that. Okay, equals the sum of the squares. So there's 12 boys. Okay, minus the mean squared over 12. Okay, so solve that. And I would keep all decimal places in any of these until you're finished, right? And then do the same for the girls. So girls was 4.3. Okay, so then standard deviation. So let's first find the variance for the class. So we need the total of all of those. So divided by 25 students, and then you need to subtract the mean of the class, which was exactly 33.6 squared. And then the standard deviation, the square root of that, and that's where we'll go to 5.86. 3 digits. think I'm just gonna leave the next one. You can do it. It's kind of similar to what we've been doing, even actually easier. Because you're given some of the data values, some of them squared. Let's go to question 7, because it's frequency chart, but with intervals. So it says, the times taken in a 10-kilometer race were noted for 80 people. The results are summarized in the following table. So notice how there is an overlap here. Sometimes you will see that in charts. So you don't actually know. That one person, I guess, could be at 80. Okay? Could be less. One of these people could also be at 80. So so sometimes in terms of graphs that you'll see, it might be a little bit, or charts might be a little bit unsure about that, but you don't really care what a particular value is. This just means they're between there. And if it specifies in a question, and I've read through the IB stuff, they'll tell you what interval to make. So if you had to come up with a set of intervals, they'll tell you do it in 10-person intervals or whatever it is. Okay. So in this case, when you enter this into your calculator, because that's what we're going to do, you would use the median value in there, which is really the average, same thing. So 60 plus 80 divided by 2 is 70. So, and this would be 90. That's what you're going to enter. You can't do an interval in your lists. And again, it's an average. You don't know the specific values. Okay. So in this case, calculator. Press everything twice. So, edit on that. Remember, you can clear your list, go up, press clear, enter, and it goes away. So I put 70, 90, 110, 130, 150. Scared over here. There we go. 1, 4, 26, 24, 10, 7, 8. Okay, so then quit out of that. We go stat, calc. It's always one variable stats, even though you're using 2 lists. And again, make sure you put in, I have to do, it doesn't prompt me on mine, but it will for you. So your X or data values are your first column, which is in list 1. And then your frequencies are in list 2. Okay. So your mean is 132.75. Now, what would they do for this? Like, it does terminate, so I think I would leave it like that. I don't think they're going to want to see 133, 3 digits. So if it terminates, just leave it. Standard deviation. So your calculator doesn't give you the standard deviation squared. It's just the 28. So this one doesn't terminate from what you can tell. So 28 point goes on beyond. So I'm going to show this to 28.2, 3 digits. Also doesn't look like they take marks off for rounding sometimes. So just be aware of that. And variance though, this is a question you guys might know this. Can we copy this? Is there a signal, like from a graph, we can copy an X and then into our calculate and do something with it. But I'm wondering if we can copy that. Does anyone know? Anyone done that before? So what is it? 28 to, I probably not on this older calculator. 389, 389. Anyway, it's gonna be to only 3 decimal points, 3 digits anyway. Oh no, it won't be. Yeah, so here, not quite sure actually what total it's at, but from what I can tell, they don't take marks off for rounding, so I'm going to go to 1 decimal place.
What was the other value like on top of sigma? That's like kind of 28.
Oh, that is the sample. Does it say the capital S?
Yeah.
Yeah, it's a form of standard deviation as well. So, yeah, but we never use it, and I know doesn't use it. So again, that's beyond our curriculum. I can't remember the difference between the calculations. They use a different n value, I think, and they summarize it for the population. Okay, so then just getting more specifics here on discrete probability. So we've already talked about this, just in terms of some of the notation. So probability of x, that's your random variable, assigned to different values. Okay, so that's the notation. So the probability distribution of a discrete random variable can be given in a table. Okay, graphically, you learned back in Math 20 a spike graph or a histogram. Okay, histogram is really similar to almost like when you're taking the integral, right? Using rectangles, right? The long way of taking the integral. And function form if you actually know the function that represents all those probabilities. The probability distribution is just a listing of all of them. So here's an experiment of tossing a coin 3 times in succession. So list all the possible outcomes. So let's do this one. We should have time. Actually, we don't have too much time today. So we'll think about H for heads, T for tails, and what you would get if you tossed a coin 3 times, all the different possibilities. If you remember back to Math 20, you might have used a tree diagram, makes it a little bit faster. So your first toss could be heads or tails. Then your second toss could be heads or tails, heads or tails. And your third toss could be heads or tails. Alright, so what can you get there? You could have all of them being heads. You could have
two heads and then a tail. You could have head, tail, head. You have head, tail, tail. So basically following each of the branches. So there's 8 possibilities. Okay, and then let x equal the number of heads. So this particular experiment is the probability of having heads in your toss. So what's the probability that x is 0, which means no heads in your toss? Okay, well, that would be 1 out of the 8. Then for 1 head, so x equals 1, that would be 1, 2, 3 out of 8. And then 2 heads, 1, 2, 3, so 3 out of 8 as well. And then all 3 heads, just once, 1 out of 8. Okay, obviously it's discrete. You can't toss half a head or half a tail, right? I'll put part of. Okay, so fill in that chart with the probabilities. So 1 8, 3 8s, 3 8s, 1 8. So in this case, probabilities are all greater than 0, okay? But you could have a probability that is 0, but just so you know, just in general, probabilities have to be between 0 and 1. Okay? And in a probability distribution, all of them have to add up to a total of 1. So the sum in a probability distribution is 1. So if you're using summation formula for the probabilities, you get 1. So that's how you can determine if something represents a probability distribution. In this case, we are continuing with this. We're going to do a spike graph and a histogram. So down on the bottom would be our number of heads. And this would be our probability, if it's a probability. If it was frequency, then you would just put the number of times, right? It's going to have the same shape, so it corresponds to a probability. You want your scale to be equal, so biggest value is 3/8. So I'm just going to do 1/8 for each of these. And a spike graph just means you plot the point and you draw a spike, a line down to that value. Hopefully a vertical. a straight line. How about I use my line feature? That would help. That's crooked. There we go. That's crooked too. And oftentimes we put like a okay, so something like that. Histogram. So in this case, these are values in order 0, 1, 2, 3. I actually would probably label the actual bars, so in between here would be 0 because they are discrete. You're not joining them. So here I'm actually going to label this 0, 1, 2, 3. And then your bars will be the same as the spike. You could actually reduce 2 8s to 1 4, right? But then your bar here, actually I can use a rectangle, I think. So I'm going to do this. Oh, I'm malicious. Okay, that's better. Tell you, man. Oh, move the whole thing. That's really good. Okay, there we go. That's better. Let's copy this one. Oh, yeah, there we go. That's great. Okay, I give up. How about this one? I think you get what I'm getting at, hopefully. It's close enough. How long can it take to do one histogram? With Ms. McKay, it takes a long time. Okay, so then these ones here explain why each of the following are not probability distributions. So that's where you are looking at some of the properties. They have to add up. Total probabilities have to add up to 1. So if I take a quick look here, these are all my possible x values of my variable. These are my probabilities. That's going to be 1 plus 0.4 is 1.4. Not going to work. Here, substitute them in. Here, find the value of k so that this is a probability distribution. And then I think that's where I wanted to get to anyway today. So got pretty close.